All right, so I'm just going to go through the solution to the final 3 practice problems from the exam review that I sent you guys at the beginning of the week. So number 6 needs the integral from 0 to 2 of 8x cubed plus 3x squared. And we're taking the integral with respect to x. So first things that we probably want to make note of, our function is 8x cubed plus 3x. The beginning of the interval is 0, and the end of the interval is 2. So when I do my calculation here for delta x, I'm going to do 2 minus 0 over n, which is 2 over n. And when I want an expression to represent the inputs for each of the heights of these rectangles, I'm going to take my beginning of my interval and add it to I times delta x. So in this case, that's 0 plus I times 2 over n, which is 2I over n. So I've got an expression for my inputs to the function, and I've got an expression for change in x. So what that means is I can rewrite this now as the limit, as n approaches infinity, of the sum of rectangles from our first through our nth rectangle of f of xi times delta x, which can also be rewritten as f of 2I over n times our delta x, which is 2 over n. What I'm going to do now is remove that constant from the sum, not from the limit, and I'm going to start to use some of my summation rules and properties of summations to make this look a little bit nicer for myself. So for starters, I can substitute that 2I over n into the actual f of x. So this is the limit as n approaches infinity of 2 over n times the sum of 8 2I over n cubed plus 3 2I over n squared. And this should be a 3x squared, although I didn't copy that down. There we go. All right, now I'm just going to simplify this a little bit. All right, that's just me cubing and squaring the appropriate terms. It's starting to get a little complicated, so it might not be a bad idea just to remind yourself what you're doing to include these brackets so that we can see exactly what that sum includes right now. Okay, so now what I'm going to do is remove all of the constants from each of the sums, and I'm also going to apply one of our properties of these summations that says that if I'm taking the sum of a sum of two functions, I can take the sum of this function and add it to the sum of this function. So I'm going to remove constants, and I'm going to rewrite this expression with one of those sum properties. So it's at this point that I'm going to take this 2 over n and distribute it back into each of these terms. The limit is still the outermost component of this whole thing, but I'm also going to replace these sums with expressions that we know are equivalent to them, again, based on those early sum laws. All right. So now what I'm going to do is I want to rearrange these expressions in here so that I can start pairing up as many of these numerators that involve n with denominators that involve n, and I'm going to push the constants into one fraction as well. So I'm going to put this 128 above the 2, and I'm going to multiply that by some other terms. So remember that since all of this is squared, I really have 2 n's and 2 n plus 1's. So there's going to be a big step from this line here into the next line, but we'll explain where they come from. So before I finish writing this here, this n here went over one of these 4 n's that are here. It's really n times n times n times n, right? One of those n's is being divided by one of these n's. The other n, because this is really an n squared, is being divided by one of these n's. Then I have 2n plus 1's that are being divided by the other 2 of these. And I'm just going to continue this process here with the second term, which leaves us with this expression. And the nice thing about this is we can see exactly what's going to happen with some of these terms. This term here could be rewritten as 1 plus 1 over n, and so could this one. So I'm going to think of that in terms of 1 plus 1 over n, and I'm going to do the same thing with this. And this one is going to be 2 plus 1 over n. So in this next and really last representation here, I'm going to consider what would happen if I did let the n value approach infinity. Well, this first term would cancel. N divided by n is 1. N divided by n is 1. N divided by n is 1. All right. So I am going to have whatever 128 divided by, oh, and that's a mistake there. That should have been 4, right? 2 squared. 2 squared is 4. All right, so whatever 128 divided by 4 is, times 1, times 1, times, and then if n is approaching infinity, then this whole expression is approaching 0. So we've got the same thing here, and here, and here. So then that would mean that this whole term is approaching 1. 1 plus 0 would be 1. All right, so times 1 and then times the fourth one, plus 24 divided by 6, times 1, times 1, times 2. And that would be altogether 40. The key to this next example is first to rewrite it. We've discussed in the past that if your a value is greater than your b value, you want to rearrange that as an integral with the greater b value. But when you do that, you need to remember to negate the value of the whole integral. All right, so we've got this expression now is the one that we're going to work through from this point forward. F of x is x squared plus x, a is 0, b is 2, delta x, again, is going to be 2 over n, and our input values for the height of each rectangle, again, are going to be 2I over n. This hasn't changed from the last example. So let's set up the limit, and then we can plug in the values. And now I'm going to remove my constant. And remember, I'm removing the constant 2 over n from the sum, but not from the limit. All right, we're going to continue here. I've also squared the 2I over n. Now we're going to apply some of those sum laws that are going to allow me to represent this as the sum of two separate sums. And of course, I can remove the constants from those individual sums as well. So it's at this point that I'm going to distribute that 2 over n constant, and I'm also going to re-represent these sums using some of those sum properties that we talked about in Appendix E. And it's at this point that I'm going to rearrange these fractions so that it just looks like a product of a bunch of individual fractions. So there's going to be some cancellation that happens. Obviously, these two expressions are very simple cancellations. But in this case, I'm going to have 1 plus 1 over n. Here I'm going to have 2 plus 1 over n. And here is another 1 plus 1 over n. So I'm going to keep that in mind when I evaluate the limit, which now I can envision what's going to happen when each of these n's approaches infinity. So when that happens, I could reduce the 8/6. That's not affected by the limit as n approaches infinity. So that's 4/3 times, I've got 1 times 1 times 2 plus 4 divided by 2, which is 2, times 1 times 1. And so now I can simplify this. And this ends up being 14/3. One thing that I have to keep in mind is that from the very beginning, I stated that since we had flipped the order here, this whole thing was going to be negative. So it probably would have been appropriate from the very beginning to have this be the negative limit. And it was probably negligent on my part not to have that there. So negative 14/3 is going to be the value of that limit. We can do this last example quickly the way we did the previous one just to keep the video from getting too long. So I'll write out our function, our a and our b value. So when I calculate my delta x, this is pretty similar. I still am going to have 2 over n for my delta x because the difference in the integral is just 2. But my input value, or the height of each of these rectangles, is going to be a little different because in this case our a value is 1, and so when I multiply I by delta x, I'm going to end up wanting to write this as 1 plus 2i over n. So that's going to be my input. All right, so I've plugged in my xi into my function, and now I'm going to remove the constant. And notice one thing we want to be careful of here is that I can't distribute this 2. Obviously, I have to expand this, and so I'm going to multiply these two binomials together. So once you multiply those two binomials, you do get this expression. This is going to be a 4i over n. And so when I distribute that 2 into each of these terms, I'm going to get 2 times 1, which is 2, 2 times 4i over n, which is 8i over n, and 2 times 4i squared over n squared, 8i squared over n squared. And obviously I'm going to combine these two like terms next. So I end up with these three terms, right? And obviously 2 plus negative 4 is negative 2. That's why I have this negative sign here. I'm applying one of my sum properties here, and now I'm going to remove constants from each of these. So I've removed the constants, and now I'm going to evaluate each of these terms, while also distributing this 2 over n into each of them as well. And so now we can rearrange each of these individual terms in the same way we have in the previous two examples. And so we're going to have some nice cancellation here with these. This here we've seen in previous examples, that's going to go to 1 plus 0. We're going to have the same thing here. And this is going to be 2 plus 0. So when I take the limit as n approaches infinity of each of these terms, I'm going to have 16 over 2, which is 8 times 1 times 1, plus 8 thirds times 1 times 1 times 2, minus 4. And I can combine all those like terms, get a common denominator if I need to do that. 28 thirds is the final sum.